Okay, for this lesson we want to generate our results based on the what these nominations. Okay, so just remember that we have the transfer function in here, both two sides, right? One of them is 1, the other is these things, but we have additional pole in here, just like this one. Okay, and so how can we define these parameters in here? Just remember that we can define the numerator in here just like this one to 5 and denominator as the 1 and 10. Okay, for this signal representation. And so we can define the TF, or we can use the TF function to generate the GS signal, or in another term TS1. This is the first system, and TF, and so 5 and 1 the num and then. Okay, these are systems. And so if I run this code, we have the 5 divided by s plus 10, or we can generate the GS1 in here with, in terms of the TF, the numerator 5 and 5, this one, and so the num and then can be given in here just like this one. Okay, and so these are the GS1 function. And so how can we create this TF in here? The feedback function can be used in here. Okay, and so the GS1 and the unity feedback can be given just like this one. Okay, and so if I run this code, and so the first system represents the open loop system. Okay, this is the open loop function, but the another term can be built with the feedback function with the unity step, just like this one. If I choose the 2 in here, and so this means that the R unity is transformed into the 2 value, and so which means that if we take a measurement of any signal in here coming from the CT, and then we multiply with the 2 and creates the total system parameter. But for the unity feedback signal we need to assign the 1. Okay, or we can build the 1 divided by s in here just like this one, but this s should be defined with the TFS. Or HS1 can be defined with the TF and 1 and 1, for example 1 0. Okay, and HS1 can be given in here just like this one. Okay, you can use it freely, but in this case we don't need to use that. We just use the 1 for the TS1 function. Okay, so just remember that we can apply the TS1 for the step signal in here. And so if I run this code, and then we will have the step results of the R parameters in here. Okay, and so the characteristic can be checked with the steady state response. For example, this is equals to the 0.5. Okay, just remember that. But this signal is equals to the to the 1 divided by s. For example, if we choose the 1 divided by s, this returns to the 1 divided by 2. But in this case we have the 5 divided by s in here, which means that we apply the 5 unit step signal in here, or in a constant term 5t. Okay, and so how can we correct these terms in here just like this one? 5 times ts can be assigned in here. Okay, and so the steady state can be checked with the what? With this value 2.5. Okay, so this is the unit step signal, unit step response figure. How can we apply the ramp signal in here? Just remember that the ramp signal 5 divided by s square, and so if this is the case, step creates the 1 divided by s, and so we should divide the terms with the what? With the s in here. But in order to do that, we need to build the what? The s signal in here. As the what? As this one. S, TF, S, right? So, in this case, this S adds the what? The one integrator term in here, because this step creates the what? The 1 divided by S. Multiplication with the 5 divided by S. If we choose the what divide with the S, and so totally we have the ramp response in here. And so this always goes to the what? To the infinity value. For example, if I choose the 100,000th value in here, it always goes to what? To the infinity values. Just like this one. Just remember that the R case generates what? The infinity value in here. Okay? And so, this can be set with no one. And so, how can we apply the what? The acceleration or parabolic response. Just remember that this must be equals to what? The 10 times TS1. And so this S is always applied the S square in here. Okay, and so this step and 10 and S square generate to the what? The 10 divided by S over 3. Okay, and so if I apply this function in here, and then we will reach to the what? The infinity value at the what? At the t goes to infinity. Okay. This is the first example of our system in here. Okay, and so first system, we have also a second system in here. Okay, what's the second system in here? 5 divided by S times S plus 5. Okay? And so, just like this one, we need to build what? The R transfer function in here. I'm sorry. And so, 5. And this one is equals to the what? The 1 divided by these terms, right? Because if this is the case, and then the 5 divided by S squared plus 5 times S should be given in here, because the second transfer function is equal to this one. And so the another term is the TS2 in here is equal to the what? The 5 divided by S squared plus 5S plus 5. Okay? These are the general representation of the R function, which is given in here. Okay, so how can we apply the another steps? We can just copy of the whole of the terms in here, just like this one, right? And so in the first place, TS2 for the unit step response, if applies, and so the R general results closing to the what? The steady state values of the 5, right? This is the final value is the 5, which means that if we apply the 5 at the input, we will get to the what? To 5 at the output, right? And so, what is the error values of these terms? Error values is equals to the what? To 0, right? But if we apply the ramp signal in here, we will get to the what? To 5 value at steady state in this case. How can we measure these terms in here? And so, if I remove the comments in here, just like this one, the TS2, okay? And so if I run this code again, and then we will have to what? This kind of signal. But just remember that this signal also goes to the what? To the infinity value, right? But this is applied with the what? With the ramp signal, which means that the characteristic steady state values is going to what? The final value is going to the what? Infinity at this time. But just remember that in this case the E or this signal is equals to the what? The input minus output signal, which means that at the infinity value, this RS at the unit at the ramp signal, we goes to the what? The infinity value. But the RCS also goes to infinity. But the difference between these two signals is equals to the what? Is equals to the 5. Okay? But in the first place, we have the infinity value between to what? To input and the output signal. This is important. Okay? So, how can I utilize the another function in here and so TS2? And so if I run this code and then we will get to what characteristics steady state is going to what? The infinity. But the difference between the input and output goes to what? To infinity value at this case. Okay? Any question? So, if there's no question, we have the example in here, just like this one. The GS is equals to the what? The K times S plus 5 divided by S plus 6, 7, and 8. And so, we will find that the K is equals to the what? The 672 in this case. And so, how can we implement this algorithm in the what? In the Matlab. Now, this is our case, okay? And so, example 4 can be written in here, just like this one. States error for KV, okay? And so, firstly, we need to define what our system with based on the what? The zeros value. We have the 1 zeros in here, just like this one, the -5, and the poles with in terms of the -6, -7, and -8, right? And also we have one more 0, right? And we have the gain value in here, just like this one, the 6, 7, 2, okay? And so we can generate the GS function in here with the based on what? The ZPK function. This is taking to what? The zeros, poles, and the gains of your system, and then generates the what? The transfer function based on these informations. And so the zeros, poles, and gain can be given in here, okay? And so if I run this code, and then the 672 times S plus 5 and S plus 6, S plus 7, and S plus 8, okay? These are the signal. And then suppose that we generate what? The unity feedback signal in here, just like this one, because we have the unity feedback in here. And so if this is the case, the TS is equals to what? The feedback function can be called in here gs and 1, right? And so if I run this code, this is the final expression for the what? For the R cases. All the poles are given in here, and then we can test this algorithm for the what? The steady state errors. Okay? And so figure and step signal can be applied to the TS in here, just like this one. And so this step is the what? The 1, right? Because we don't have any coefficients in here, and so the 1 divided by s is applied to this system in order to what? To produce the 1. And so if I run this code, and then we have this kind of inputs, and so the characteristics can be checked with what? The steady state values. And so the final value is the 1, because we have the 1 integrator at the poles. Okay? And so there is no error between the input and the output signal. In this case, whatever we take or select the K in here. Okay? But if I choose to apply to what? To TFS in here, 1 divided by S in here, just like this one, for a given 1 ramp inputs in here. And so if I run this code, and then we will have the what? The characteristics at the what? The infinity values. But if we apply the 1s or the T signal in here, just like this one, we have always difference between this step signal with the ramp one. Okay? And so how can we calculate these values based on these informations? Just remember that we can generate our responses in here. Time and output can be obtainable. Output is the step TSNS, right? And so if I run this code, we can comment all the terms in here, and so the plot, time and output can be given in here, right? And so if I run this code, and then we will have these terms in here, and also we can take the 50 seconds value in here, just like this one. Okay, this is the R response for R signal, and so the figure can be given in here. Also we can generate the T signal in here, just like this one, 0 to 0.001, for example, the 50 seconds in here. Okay, and then hold on, can be given in here, and so T and T can be given in here because we have the time signal as the ft is equals to T. Okay, and so if I run this code, and then we will have the what? These outputs, and the legend, the real, and the input or the output signal. Okay, and so just see that this signal always constant between these two value, right? And so what is the last value, last error value in here? We can calculate it with the what? With the output and minus T, and returns to the what? To the R signals. And this cannot be true because it's not answered. 0, the output 50 values, the t. I'm sorry. We should check the same time values in here, just like this one. The time, in this case, 40.9 value in here, but at this t, just see that we have 50 value, right? You see the difference between this time, because the last value is what, the 50, but the other time is the 49.9, right? And so we need to get the in this values of the what, the 40.9, right? And so at the t, which is equals to the what, these terms, just like this one. And so see that output and the t, okay, t 49901, okay, this must be true. And so if I run this code, and then voila, 0.1, see that? Do you understand the wrong results in here? Because in this case we have the t value in here 0.9.9, and so this time at the end of this code 0.49.9. See that this t must be removed from this time, okay? Any question? This equals to what, the 0.1. Do you understand what I'm trying to do in here, guys? Everything is okay? Any question? Okay, that's all for the state response. That's the end of our lesson for today. Okay.